For this video, we're going to talk about tangent plane approximation and differentials. This is the kind of the generalized notion of tangent lines, approximations, and differentials for functions of one variable. Let's go ahead and review tangent lines just as a quick refresher. So suppose we're looking at a function of one variable, so we have y is equal to f of x. So we can recall the tangent line at the point a f of a is given by the equation y equals f of a plus f prime of a x minus a. So if we let L of x be f of a plus f prime of a x minus a, this is the linearization of the function at a f of a. So we can see that in the picture here, that the blue here gives us the curve y equals f of x. We look at this point here, a f of a, and then the tangent line here is the red line, which is given by y equals L of x. So we want to go ahead and generalize that notion to surfaces. So the first thing we need to talk about are what planes in 3 space looks like. So recall from before, we saw a plane as an equation of the form z is equal to c1 plus c2x plus c3y for c1, c2, and c3, some constant numbers. Now, in general, if I want to look at, so for when we were looking at, say, for tangent lines above, we didn't want just like y equals mx plus b. We wanted to focus on this x minus a because we were interested in the a component. So for the plane, we might want to do the same thing. So rather than just having this form with an x and y, we might want to isolate the a and the b here and write our plane in this form instead. And we can always write a plane in this form. So to check this, if you just take d to be c1 plus c2a plus c3b, d2 to be c2 and d3 to be c3, they give the same thing. So you can check that if you'd like by just plugging in, but the main point here is that we can represent our planes in this form for any a and b. So we can kind of shift how the function is defined to make sure we're focusing on what's happening at the point ab. So if we recall from the partial derivative section that if we're given any surface z is equal to f of xy at a point, and we look at a point ab, there's a plane that's tangent to the surface at that point. So here we see our surface here is the green surface here, which is given z is equal to f of xy. And if we look at this point AB, this dot up here is directly above that on the surface, and this blue color plane here is the tangent plane at this point AB. So it just touches the surface there, just like a tangent line would just touch a curve. And so this is some plane z is equal to L of xy. And what we'd like to do here is we'd like to figure out what is an equation for this plane. Just like we had a nice way to figure out the equation of a tangent line based upon the value of the function and the derivative of the function, we'd like a way to figure out the equation for this plane z is equal to L of xy based on the value and then the derivatives at that point, if possible. So let's go ahead and go through and see how we get this. So we'll go ahead and let L of xy denote our tangent plane, and we're going to write it in the same form that we had before, where we're kind of focused on the a and the b. So what we need to do is we need to figure out what d1, d2, and d3 are in terms of our function f. So the first one's fairly easy to get. Notice if I plug in a and b up here to this equation, I get an a minus a here and a b minus b here. So both of these terms drop away to 0, so I just have d1 left over. On the other hand, though, we saw on our picture above that L of AB and F of AB have to be the same because they're tangent at that point, so they go through that same point. So we also have L of AB is equal to F of AB. So if it's equal to D1 and it's equal to F of AB, that tells us D1 is equal to F of AB. So we figured out this form here. That's the value F of AB. So now we need to figure out what D2 and D3 are. And if it's going to follow the same pattern that the tangent line is, those should have something to do with the derivative of f. So let's look at how that works. So let's look back at our surface and let's fix the value for x. So we're just going to fix the value a. So we see here the green surface again is our function overall. And then if I look at fix all the values of x to be equal to a and only let y change, it gives me this orange curve here. So all of these values on here have x just to be equal to a. Now y is still changing here. So now let's go ahead and throw the tangent plane onto that same picture. So we have this green surface again. I have this value where z is equal to to f of ay, so this curve where x is only equal to a, and then I have my tangent plane on top of that again. So finally, let's add the curve where for the tangent plane we also fix a to only be, or x to only be equal to a. So in that case I have this curve here, the purple one going down is where I fix x to be a for the tangent plane as well. And so we notice here, this is something special is going on here. We have this tangent plane. If we fix this value of x to be a, we get this orange curve. If we fix the value of x to be a on the tangent plane, we get this line here in the tangent plane. And we can see from this line here is the tangent line to this curve, to the orange curve. So if we plug in x equals a, the d2 times x minus a becomes d2 times a minus a, so that goes away. So I'm left with just this equation here. So this is the equation of a line. So as I just said, the curve z is equal to L of ay is exactly the tangent line to the curve z is equal to f of ay. And that's exactly how we define the partial derivative. We said the slope of that tangent line to the curve when we fixed the value was exactly how we define the partial derivative with respect to y at ab. So using those two things, we see the slope of this line must be the partial derivative, so d3 must be equal to f sub y of ab. So that tells us what d3 is, and we can go through the exact same argument by fixing y to be equal to b, and that will show d2 is equal to f of x a comma b. So you might want to pause the video and kind of run through that and make sure you understand how that whole argument works. Just go through the same thing we did where we fixed x to be equal to a. In this case, let x be the variable and fix y to be equal to b. So what we've derived here is that the tangent plane to our surface z is equal to f of xy at the point AB is given by this equation here. So this was our d1, this was our d2, this was our d3. So we do get the d2 and the d3 are derivatives. It's just in this case, since we have two variables, we don't have a derivative, we have two derivatives at least. We have the derivative with respect to x and the derivative with respect to y. So we get those derivatives since we have two of them. So we can compare this to the formula for the tangent line. Notice the constant term, again, is the value of the function. And then we have the x minus a has out front the partial derivative with respect to x. And the y minus b has the partial derivative with respect to y out front. So they look very similar. We've just added a variable in, so we get a little bit more complicated expression, but the same type of format. So just like we saw when we studied tangent line approximations, that we could use the function. So if we had a value of a where we could evaluate f of a, and we had a different value x0 where we didn't know how to evaluate f, we could evaluate L at x0, and that would be pretty close to f of x0. So we can do the same type of things with tangent planes. So if we have a point AB close to this value f x0, y0, where we're trying to evaluate f of x0, y0, if we can evaluate f at AB, then we can say we can find the tangent plane at AB, and then the f of x0, y0 will be pretty close to the tangent plane value of L of x0, y0. So you can go ahead and see this in a picture here. So in this case, the red surface is our z is equal to f of xy. The green here, if we go over to the point AB, so this is something that we would pick where we could actually evaluate f at that point, and then we would find the tangent plane there, which is given by this green surface. And then if we go over here to x0, y0, I might not know how to figure out what f of x0, y0 is, but I can say it's going to be approximately equal to L of x0, y0. And the smaller the delta y and the delta x is, the better the approximation will be, just like it was with the tangent line case. If you had a smaller delta x, you had a better approximation. And finally, the other topic we had when we were doing tangent lines was differentials. So let's refresh our memory on this as well. So we'll take y equals f of x, a function of one variable. So recall we fixed some values a, so a is generally where we can evaluate f at, and x0 is a value where we wish we could evaluate f at, but we don't know how to. So we set dx to be the difference between these two values, so x0 minus a. We set delta f to be f of x0 minus f of a. So this is the quantity we don't know how to calculate. Because if I knew how to calculate delta f, I could just add f of a to delta f, and that would give me f of x0. So delta f is what we're interested in. This is the exact change in the function. df, on the other hand, is L of x0 minus f of a. So this is by equation for L of x, if we just plug in x0, we see this is equal to f prime of a x0 minus a. So we denote this as df. This is the approximation to delta f, and we can actually calculate df. So we used in our examples back in this section when we studied differentials of one variable, we used that delta f is approximately df, which is f of x0 delta x, or it should be, sorry, this should be f of a delta x, the a coming from here, so this should be f prime of a delta x, and this is something we can actually calculate. We probably can't calculate f prime of x0, so that should be an a, it's a typo. So again, delta f is the exact change, df is the approximate change. So here's a picture of what's going on here. So I can evaluate here this a f of a. And since I can do that, I can also figure out what this tangent line here is, the y equals L of x. Now over here is the x0. This is what I want to evaluate. So up here is f of x0. So we see the height here, f of x0, minus the height here, f of a, is the length of this line here. And that's our delta f. That's what we wish we could evaluate. We can't do that though, but we can evaluate L of x0. So I can figure out what this height is. And so this height minus this height is the one that I can evaluate, and that's df. So what we're saying here is the delta f is approximately df. And the smaller the delta y, you can see if you were dragging this over, this would be going down here, and this would be coming down here, and they're beginning to be better and better approximations. So that's what we learned when we were doing functions of one variable. And we can take the same idea now to more variables. So let's say we've picked a point A, B, and just like with the tangent plane approximations, this is something where we can evaluate f of a, b. We're going to fix a point x0, y0, for which we're interested in the value of f of x0, y0. Set dx to be delta x, which is x0 minus a, and dy to be delta y, which is y0 minus b. We're going to say delta f is the exact change, so the change in f, so the difference between what I want to know and what I do know, and df is going to replace the f of x0, y0 with L of x0, y0. So this is the one that I can actually calculate. So delta f, the one I wish I knew, df, the one I can calculate. So now if we recall the formula for what the tangent plane approximation was, it was given by this equation here. So notice if we put in x0, y0, here, if we look at what's going on here, so L of x0 minus f of a, we would go ahead and get rid of this f of a will cancel out, and then I'll get an x0 minus a, which is delta x, and a y0 minus b, which becomes delta y. So maybe pause the video here and make sure you understand where this is coming from. You're just looking, df is the difference between these things, so go ahead and plug x0, y0 into this equation, subtract f of ab from it, and check and make sure you understand where this equation here is coming from. So just as in the case of a single variable, we have delta f is approximately df, and now the df is given by this equation here. So in the single variable case, we had f prime of a delta x. In this case, we have a change from the x changing and a change from the y changing. So we have both terms that we have to add together. So let's go ahead and look at a picture of this, which is a little bit more complicated, difficult to draw. So if we start here with AB with something we know, so we go up here to f of AB here. So then I have my surface here, z is equal to f of xy is the red surface. The green surface again is the tangent plane at AB. And now what we've drawn here is I go a little delta x, a little delta y, I get to a new point x0, y0. That's the point I'm interested in. Now this somewhat transparent blue plane here stays at the height f of AB all across here. So the difference between this height and this height is df, the difference between what I can calculate, L of x0, y0, and f of ab. Now we go up here to f of x0, y0, what I wish I could calculate. We make a plane here that stays the same height all the way across, and we can see the difference between the f of ab and the height of this plane, so f of x0, y0 minus f of ab is exactly the delta f. And the idea is we're approximating delta f with df here. So this picture is not a great picture in terms of saying that these should be pretty close, but it does give you an idea of geometrically what's going on when we're looking at our differentials here. And this is fairly difficult to draw on the board by hand, so this picture should hopefully help you understand what the different quantities are measuring here.